In this lecture, we will explore more of the wow moments that made the DeepSeek R1 model highly efficient and cost-effective. One major reason behind its efficiency is the use of dynamic compute power. This means the model adjusts the number of neural networks it activates based on the complexity of a question. For example, if the user asks a simple question such as, "What are weights?" the model will only use around 2 neural networks to generate the response. However, if the question is more complex, like explain the Higgs mechanism in superconductivity, the model recognizes the higher difficulty and activates a deeper network, perhaps around 12 neural layers, to provide a thorough explanation. This technique, known as adaptive computation, allows DeepSeek to allocate more resources for complex problems while using fewer for simple ones. As a result, it saves significant computing power and reduces operational costs. Another key improvement came from reinforcement learning with human feedback combined with curriculum learning. Despite being trained on massive datasets, language models sometimes produce unsafe or unhelpful answers. To correct this, DeepSeek adopted a human-guided reinforcement learning approach. The training process began with simple tasks and gradually progressed to more challenging ones. During this process, human reviewers evaluated the model's responses. Helpful and safe answers were rewarded, while harmful or misleading outputs were penalized. For instance, if a user asked, "How can I lose weight?" and the model replied, "Stop eating entirely," humans marked that as unsafe. The model then adjusted its internal weights to avoid producing such responses in the future. When a better answer like, "Maintain a balanced diet and regular exercise," was generated, it received positive reinforcement. Over time, this human-in-the-loop training helped DeepSeek generate safer, more useful, and human-friendly answers. DeepSeek also implemented counterfactual data augmentation to reduce bias. Bias can occur when training data is unbalanced. For example, if most of the data refers to men, the model may unconsciously favor masculine perspectives. To fix this, DeepSeek created mirrored versions of the same data by swapping gendered references or other biased attributes. Imagine a training sentence that says, "Nurses are caring while engineers are logical." This phrasing can lead the model to associate caring only with nurses and logic only with engineers. To counteract that, DeepSeek generated an alternative version: engineers are caring while nurses are logical. Training on both variations teaches the model to treat these roles equally, helping it understand that caring and logic are not bound by gender or profession. This counterfactual augmentation strategy balanced the dataset and significantly reduced bias in model responses. In summary, DeepSeek R1 achieved its remarkable efficiency and reliability through dynamic compute allocation, reinforcement learning guided by human feedback, and counterfactual data augmentation. These innovations allowed the model to produce safer, fairer, and more accurate outputs while keeping computational costs low. In the next lecture, we will explore how these design choices further improved the model's scalability and performance across multiple tasks.